Okay, it's 4:30. I think before the seminar, I would like to give a very brief, introduction for the Professor Aurelien Manchon. Actually, his research focuses on the field of the theoretical spintronics and aims at identifying novel mechanisms that can be used for operate spin-based devices. His research interest spans from spin-orbit torque to the chiral magnetism, anti-ferromagnetics, and ultra-fast spin dynamics. I think Professor Aurelien Manchon is a pioneer in the spintronics for the SOT based and also Rashba. He has also for the review papers on the SOT and the Rashba effect in the model review of physics. I think the rest is unless have pass the time to the Professor Aurelien. Welcome to give us the presentation today. Okay, thank you
very much, Vincent.
Time is you. Yeah.
Thank you very much for the nice introduction. It's really my honor to present this. My work at NUS. It's a very prestigious place, and I've been having great experience with collaborating with my friends over there. So it's really a pleasure to come and talk to you today. So what I'm going to talk about today is about theory of spin-orbit torque and Dzyaloshinskii-Moriya in van der Waals magnets. So I'm sure that you are all experts in van der Waals systems and magnets, way more than I am. So this work is essentially a collaboration between my former postdocs in KAUST, Kyunwan Kim at KIST in Korea, and Stefan Roche and Jose Garcia in ICN2 in Barcelona. So I will start, sorry, let me get rid of that. I will start by a video. So you probably, if by any chance you attended already one of my presentations previously, you probably already know this video. So I apologize if you sing that again. But I think that's a great example of what we try to do on the theoretical side or even experimental side in spin-orbitronics. Try to harvest the coupling between the spin and the orbital degree of freedom. And I think, I'd like to show you this video that is that actually dates back to 1997. So maybe, well, hopefully some of you were not born at that time. So that was actually the selection of the World Cup, the 98 World Cup. And here you have Roberto Carlos, you have the French guys here, and as you know that this is like the very last action of this game. And Roberto Carlos is basically shooting at the goal here, Barthez. And to reach the goal, he basically makes the ball rotate extremely fast and the ball enter the goal. We'll just do that again. Look at that. So it rotates so fast that basically it enters the goal. He actually hits the corner of the goal before entering. Some researchers have investigated this effect to try to understand why he actually marked the goal at that time. And so I encourage you to have a look at this paper that is focusing on these effects. So they actually have investigated this effect on several balls. So, table tennis ball, golf, tennis, soccer, you name it. And their conclusion is that the reason why Roberto Carlos was able to mark these points is because the weather was humid. So because of the humidity, the friction between the rotating ball and the air around was very strong. And then the transfer of angular momentum was stronger. And then he was able to curve the trajectory of the ball so strongly that basically at the end of the day, we lost. So this effect, of course, is known to all of you, I guess. This is called the Magnus Effect. And that was discovered by Heinrich Magnus in the 19th century. And essentially, it works this way. So imagine that you have a flow of fluid, could be liquid, could be air, anything. You have a flow of fluid, and you have a rotating ball or rotating cylinder or rotating shape inside that. And what you're going to find is that the difference of velocity between the air the relative velocity between the fluid and this cylinder here is actually much higher on top than on the bottom. Okay, because you have rotation plus translation. As a consequence, the pressure is stronger on the top because the velocity is larger than on the bottom because the velocity is smaller. So the difference of pressure will actually create a force that reorients the ball, that basically pushes the ball on the side. So that's essentially what Roberto Carlos was using during this game. If you want to kill these effects, then you can ask the American football players, the quarterbacks. Usually, when they throw the ball, they have to make, they place their hand in this particular way to actually make this oval ball rotate around the trajectory. Then, if the angular momentum is aligned on the trajectory, then essentially the pressure is the same on both sides, and well, nothing happens. So you don't have the Magnus effect. You can actually kill it. You could also exploit the Magnus effect. And this was done in, I think, the beginning of the 20th century, where you have this ball here with those very large cylinders that rotate and that dragged the boat along the wind. So this is actually the more modern version. So this is something that is technologically working. They have also tried to translate that to planes, and I think this is the only example of a plane with of Magnus Effect driven plane, and I understand that they actually never really worked. So if you want to know more about this, the application of the Magnus Effect, I encourage you to have a look at these papers here. What I want to focus here is on the spin-orbit coupling. So how can we exploit Magnus Effect at the level of condensed matter? So I'm just going to remind you a bit what is spin-orbit coupling. So I'm sure again that most of you are very familiar with spin-orbit coupling. So let's imagine that you have a charged particle traveling with a momentum p in an environment where I apply an electric field. Then in the frame of motion of this charged particle, this particle will experience magnetic field. So this is really, magnetic field is really a relativistic effect from this point of view. Now we know that the electrons actually have intrinsic degree of rotation, not only electrons, by the way, but I mean, here we care about electrons. And in this case, the spin of the electron will tend to align on the magnetic field that is felt by the electron in its frame of motion. This coupling between the spin of the electron and this magnetic field can be expressed this way. So that's really the general form of spin-orbit coupling. Of course, you can actually go all the way back to Dirac equation and expand Dirac equation to the lowest order in electric field, and you're going to find the same Zeeman-like coupling. So here you have the spin, here you have the potential gradients, which is the electric field. So spin, potential gradients, and the electron momentum. Now, what is interesting is that when you look at a material, the potential gradient is mostly of spherical symmetry. Okay, it's actually the gradient is stronger close to the nucleus. So when you have an electron traveling, a block wave traveling in a crystal, the spin-orbit coupling will be mostly efficient close to the nucleus of each atom. In this case, you're going to have a spherical symmetry, which means that the gradient would be mostly radial. And in this case, what you end up with is a spin-orbit coupling on the form S.L, which is something that you're probably very familiar with, which is called the Russell-Sanders spin-orbit coupling. So this is really the spin-orbit coupling that is felt by the block waves. Even if you actually are close to an interface, the spin-orbit coupling itself will remain of this form. Okay, and there was some confusion at some point with where Rashba spin-orbit coupling would come from close to an interface. But really, the fact that close to an interface, the potential gradient is not spherical anymore is only a small correction compared to the atomic spin-orbit coupling. So you could say in a very good approximation that the spin-orbit coupling is mostly an atomic spin-orbit coupling in even close to interfaces. Actually, what stops changing close to an interface is the form of the block wave. So now if I project this spin-orbit coupling on the Bloch wave of my crystal, I end up with an effective momentum-dependent Zeeman term. Okay, so I'm going to have the coupling between the spin of my Bloch wave and the magnetic field experienced by this Bloch wave. And this magnetic field depends on momentum P here. Now, you basically can categorize this coupling in two categories. So if you have inversion symmetry, then this effective magnetic field should be even in momentum. If I just reverse the momentum, I should have roughly the same magnetic field. I mean, exactly the same magnetic field because I have inversion symmetry. And in this case, of course, if I apply a current in my system, the positive and negative momentum compensate each other, so nothing really happens here. However, the velocity of my Bloch state will acquire an anomalous velocity. And this one is actually very robust. It's a very robust effect. You see that this anomalous velocity depends on the spin projection and is proportional to the Dirac curvature. So this is something, again, that's, I think that is very popular in condensed matter physics at the moment. And concretely, what you're going to have is a Magnus effect on the spin level. So electrons rotating one way will be deviated along one particular direction, while electron with the spin projection that is opposite will be deviated along the opposite direction. So if you send a charge current along one particular direction, you will end up, if you just change that, you will end up with a transverse pure spin current. Okay, this is called the spin Hall effect. Now, if you have inversion symmetry breaking, so let's say you're close to an interface or you are in a crystal where inversion symmetry is broken, like of course strained gallium arsenide or in Waals structure, for example, then you see that the momentum dependent magnetic field becomes, well, basically is not symmetric anymore, and you actually have a part that is odd in momentum. It's not purely odd in momentum, but you can have a part that is odd in momentum, which means that if you send a current through the system, you can the positive and negative momentum will not compensate each other. And then you end up with creating an effective magnetic field out of equilibrium. And this is called the inverse spin Galvanic effect. It's also called the Rashba-Hildesheim effect. I'm more comfortable personally with using this long and ugly term, because then we do not enter in all the debates of who discovered what first. So inverse spin Galvanic effect. So those two effects will actually be the source of all the physics I'm going to talk about today, even Dzyaloshinskii-Moriya in a sense. So you see that in one case, I'm going to create a pure spin current. In the other case, I'm going to create a magnetization that is out of equilibrium. So it's really a spin density. It's not a spin current. There is no motion of the electron. I mean, the electron move along the direction, but the spin itself is this current of charges will create a density of electron that is out of equilibrium. So so when we actually react that we could use this effect to inject spins and manipulate magnetization, we actually started to focus on this kind of system where you have a heavy metal that is able to provide strong spin-orbit coupling, and you have a ferromagnet here. And we have been basically focusing what happened at those interfaces. So I will not talk about those particular material, but the important message here is that at this interface, you're going to have the inverse spin Galvanic effect, so the creation of a spin density out of equilibrium rather than at the interface. And inside the heavy metal, you're going to expect to have spin Hall effect. So at the end of the day, this ferromagnet will receive a lot of spin current and spin density from the heavy metal here, and that will result in spin-orbit torque. So the possibility to manipulate the magnetization by injecting a current in the plane. Now, there is always a companion effect to spin-orbit torque, which is called the Dzyaloshinskii-Moriya interaction. I will talk a bit about today, a bit about it a bit later. So the idea is that because you have inversion symmetry breaking at the interface, if you create a gradient of magnetization, then this gradient will adopt a certain chirality. So basically, if you create a magnetic domain wall, this domain wall will prefer to be, let's say, a homochiral nail wall rather than a block wall, for example. And if you create a defect, this defect will tend to, let's say, a two-dimensional defect, like you just rotate locally the magnetization. This defect will tend to prefer to be in the skyrmionic configuration. which is basically kind of a homochiral magnetic defect. So this spin-orbit torque has been observed in many materials, mostly, of course, magnetic metal heterostructures, magnetic insulators, non-centrosymmetric magnets like galvanized manganese, manganese nickel antimony, and more recently on antiferromagnets. I'm not going to talk about antiferromagnets today, but of course that's a huge direction of research at the moment. There have been also a lot of proposals, for to apply this spin-orbit torque and in different classes of devices. So because you can switch magnetization, you can imagine to create memories out of that. And that actually has an interesting advantage because you actually inject the current in the plane and you can detect the magnetization state out of the plane. So you really decouple the injection and the detection, which could actually be an advantage compared to the regular spin transfer torque memories. You can also excite gigahertz magnetic excitations. If you actually use antiferromagnet, you can even go to the terahertz excitation, which is very hard to do with spin transfer torque, but it can be in principle done with spin-orbit torque. You can also move magnetic domain walls, and if you use spin-orbit torque, the velocity of the domain walls would be probably 2 orders of magnitude larger, and this is actually what has been observed. I think the latest record is 1 kilometer per second. So it's actually extremely fast. So then you can imagine making your racetrack memories out of that. And finally, the advantage of spin-orbit torque is that, again, you inject the currents in the plane. So you have the ability to create non-local spin valves using, for instance, magnetic insulators. Then you can imagine to make interconnect spin logics and so on. So this is something that we try to review in this review here. So the topic of today is to present the work that we've been doing on two-dimensional magnets specifically. So I'm sure that you're all very aware of, well, I mean, you guys are basically one of the world experts institution in two-dimensional systems. So there have been, of course, a lot of claim and a lot of publications about two-dimensional magnets with Curie temperatures from, well, a few Kelvin to even above room temperature. So I'm just throwing some of the information here, but again, I'm sure that there are experts in the audience about that, so I will not talk too much about it. Well, what is actually interesting for me is that those two-dimensional magnets, if you just look at this guy, for example, those two-dimensional magnets are, I would say, usually you have a transition metal elements. Here you have chromium, and here you have iron. Here you have actually 3 irons here, and they are usually embedded between 2 similar halide, like iodine here, or chalcogen elements. Okay, here you have tellurium here. Here you have manganese, and the green here is selenium. So what is particularly interesting is that you can imagine to engineer the structures to induce Rashba spin-orbit coupling. So you have the smallest magnet possible, the thinnest magnet possible, and you can even induce Rashba spin-orbit coupling by making sure that the 2 chalcogen elements or the 2 halide elements are dissimilar. So if you have, let's say here, your vanadium or manganese atom, and here on each side, your selenium and tellurium, then you can actually induce a Rashba spin splitting in the band structure. And if you project the band structure on the spin density, you can have this particular spin momentum locking. So this is, for example, this is just extracted from this pioneering paper from my collaborator Udo Schwinger's-Logel at KAUST, where they actually show the Fermi surface that has been projected on the spin on the spin operator. So here you have spin X. Here you have so you have SX, so the X projection, and the Y projection. And if you actually look into that, you will see that you have a spin momentum locking that definitely is similar to the one you would expect from a Rashba spin-orbit coupling. What is even more exciting is that a few years ago, there have been actually a few publications that have demonstrated that it's indeed possible to create two-dimensional transition metals dichalcogenide with dissimilar chalcogen elements on each side. So I encourage you guys to have a look at those papers if you are not already familiar with that. These structures are called the Janus monolayers, because you know, like the god Janus that has two faces, two dissimilar faces. What is shown in this picture here is that, so this is the second harmonic generation signal, and that it shows that if you have basically what they call the randomized MOSSE, so where basically S and SE are completely randomized on top and the bottom, so basically you have inversion symmetry. In this case, there is no electric polarization, but if you actually make selenium on top and sulfur below, you end up with a strong perpendicular electrical polarization. So this electrical polarization is at the origin of the Rashba spin splitting, which is what we want. So what we did is that we picked one two-dimensional magnet. So when we started this project a couple of years ago, it was at the very beginning of all these publications. And what we wanted to do was to select one material that would be magnetic at room temperature, and that would a priori be a good candidate for Janus monolayers. So at that time, there was this paper by Bonilla and co-workers that claimed to observe magnetization in vanadium-based diselenide. So we thought, okay, that was actually a good platform to start with. So we took this system. We actually verified that from the DFT point of view, this is indeed stable. It has magnetism here, and so we have vanadium here. We have tellurium on top, selenium below, and then we can play with the different chalcogens. So of course, the first thing to do is to verify that everything is stable, that the magnetization behaves properly, and what you can observe if you just focus on this graph here. So the black dots are the magnetic moments for different chalcogen elements. So the first half here is the symmetric system, you know, VS2, VSE2, VT2, and the second half is the Janus system. What you observe is that when you go for sulfur to selenium to tellurium, you have an increase of the magnetism of vanadium that correlates with a decrease of the charge density of vanadium. So basically, because tellurium is more electronegative, it's going to suck electrons out of vanadium and then increase the magnetism of vanadium. So this is actually an interesting effect. And because of that, it's going to distort, tellurium will actually distort, sorry, if you actually go to the Janus configuration, where now you have two dissimilar chalcogen elements with dissimilar electronegativity, you're going to go for a very symmetric vanadium d orbital to an asymmetric d orbital, and that's what we want, because if we have asymmetric d orbitals, it actually means that that we basically have a charge transfer that is asymmetric between the vanadium, the top, and the bottom, which should result in Rashba spin-orbit coupling. So this is what we do. We actually calculate the band structure. Here I'm just showing the band structure of vanadium, selenium, tellurium. Okay, so this system here. And we project this band structure over on the p states of selenium, p state of tellurium, and d state of vanadium. So here you have the band structure, and here you have the Fermi surface. The Fermi surface that is projected over the SX component of the spin density. And what you observe is that there is a nice anti-symmetric SX component along this is the KY and this is KX. Now, if you actually project along SX, SY, you're going to have the same picture rotated by 90 degrees. So that's really what Rashba should give you in this system. So we have it in selenium, we have it in tellurium, because of course they have a symmetry broken environment. And most importantly, we also have this spin momentum locking in vanadium. So that's what we care about. Why? Because what we want is to be able to switch vanadium. So if we want to be able to switch vanadium, we need vanadium to experience inversion symmetry breaking and then to experience Rashba spin splitting. So you can actually quantify the momentum locking, the spin momentum locking, and actually look at the way it evolves. And of course, it increases when you have dissimilar chalcogen elements with the largest difference in electronegativity, which kind of makes sense. Of course, we can also develop a time binding model to understand where this spin splitting is coming from. And we can interpret this spin splitting coming from the coupling between the pz orbital of tellurium, or I would say the dissimilar coupling between the pz orbital of tellurium, the pz orbital of selenium, and the d, y, z, zx orbitals of vanadium. So this is actually quite nice. We can get the, at least in some approximations, we can get the block states, project the spin-orbit coupling on those block states, and we end up with a spin-orbit coupling that really looks like the one you would expect from a Rashba spin splitting. Now we move on and look at the nature of the spin-orbit torque in this system. So the first thing to do is to, first thing really is to first analyze the symmetry. Because you may, if you're familiar with spin-orbit torque, we usually parse spin-orbit torque into what we call the field-like torque and a damping-like torque. I'm going to come back to that in 1 minute. But the problem is that when you have a crystal structure that has peculiar symmetries, like here we have a C3V bond group, then the torque can be completely different from the field-like torque and damping-like torque that you would expect in cobalt platinum, for example. So in our case, we just apply this analysis on the torque, and what we obtain is that the torque in principle possesses two components. So one component, this is the effective field driven by the electric field. Okay, so the effective magnetic field driven by the out of equilibrium charge current. So the first term we have is like a field. You see, it's a magnetic field that has a direction z cross e. So E, let's say, is the field that I apply, is the electric field I apply in plane. Z is normal to my two-dimensional Janus monolayer, and I end up with a magnetic field that is simply z cross E. So that would be along, let's say, the y direction, transverse to the current to the direction of injection. Now, if I look at the field that is odd in magnetization, I'm going to have a second term that is called the damping-like torque. So this is something that is well understood in the context of transition metal interfaces. So this is not very surprising. There is even some anisotropy here, so everything is well controlled. What is more surprising, or more, I would say, unexpected, or more interesting, is this last torque here. And this torque is, you see, as a very peculiar, I mean, this is not a torque, it's a field, sorry. The field has a very particular symmetry. It only exists when the magnetization is in plane. So you can find this torque in all C3V systems. So typically, Janus TND monolayers. You can also find it in iron germanium tellurium. I'm going to come back to that in 1 minute. And actually, this was something, and just a bit of publicity. This is something that was discovered by Professor Chen in the L11 phase of cobalt platinum. I would say, but if you take a bilayer of copper platinum, cobalt platinum, you realize that this torque is actually present because you have the same bond group applying at the interface. And in this case, as shown in this paper, you can actually switch the magnetization without an external field. So that's actually a very important advantage of this kind of torque. So of course, when we saw that, we were very excited and thought, oh, okay, let's look at this torque in this Janus monolayer. So we actually collaborated with Stefan Roche and Jose Garcia from ICN2 in Barcelona. And so we basically take the Hamiltonian, perform the Vanier projection to convert to basically obtain an effective Hamiltonian that we can inject in their wave packet propagation code, and they calculated the torque out of that. So of course, the torque depends on the direction of the magnetization, whether the magnetization is in plane or out of plane. We're not comment too much about that. This is just an isotropy, and that's kind of expected. But what is unfortunate is that this torque is actually zero. It's not present. It should be present by symmetry, but it is not present when you do the calculation. And the way we understand it is because to have this torque, you need the block wave that participates to the transport. You need this block wave to experience the symmetry. So basically, you need to imprint the bond group of your crystal into the block wave. The problem is that if your transport is dominated by the gamma point of the Brien zone, where the gamma point by definition has this spherical symmetry or the cylindrical symmetry in our case. So in this case, the block state at the gamma point doesn't really see exactly the threefold symmetry. So it means that if you have a two-dimensional magnet that is dominated by, let's say, K points or M points, then maybe you're gonna have more chance to observe this interesting torque here. So I'm gonna move on now to a different aspect of the same two-dimensional Janus monolayer, which is the Dzyaloshinskii-Moriya interaction. So what we want is to quantify now the exchange interaction between local spins in this system. So we still have our two-dimensional TMD, the same one with vanadium and with dissimilar chalcogen elements. And what we expect that at this interface, we should actually have, of course, the regular Heisenberg exchange between neighboring spins, but we should also have anti-symmetric exchange that is called the Dzyaloshinskii-Moriya interaction. And this exchange, when it is strong enough, can stabilize chiral magnetic textures. So I'm going to talk about that in one minute. So the first thing to do is, of course, to extract this coefficient, the Dzyaloshinskii-Moriya interaction, from first principles. So the details of the procedure is written in this manuscript here. Essentially, what we do that we calculate the dispersion. We create a spin spiral on in K space in our monolayer, and we calculate the dispersion of the spin spiral as a function of the momentum using the generalized block theorem approach. So that actually gives us this black curve that you don't really see. This is right below the red points. Then we turn on spin-orbit coupling and calculate the dispersion at the first order in spin-orbit coupling. And of course, what you obtain is something very similar. So you see that it kind of looks like the spin wave dispersion, like quadratic dispersion. It's a bit different, but it's, I don't want to talk about those features, but now if you actually take the difference between those two guys, you're gonna have the anti-symmetric part of the dispersion. That gives you, in the limit of small wave vector, that gives you the Dzyaloshinskii-Moriya interaction. Okay, so this is the way we extract the Dzyaloshinskii-Moriya interaction for first principles. So we do that using the FLIR code that has been developed by the Jülich group in Germany. So when we do that, we extract all the magnetic parameters of our system. We end up with all those parameters here: exchange, anisotropy, Dzyaloshinskii-Moriya interaction, magnetic moment. And what we get, so we actually do that for the three Janus monolayers. We actually get that vanadium, selenium, tellurium as an easy plane anisotropy. And I really insist on the fact that it is an easy plane, it's not an easy axis, it's an easy plane anisotropy. And the vanadium, sulfur, selenium as an out of plane anisotropy. Quite weak, by the way, but still out of plane. So what we do now that we inject, inject those parameters in is a homemade atomistic spin modeling code, where basically it's gonna track the behavior, the dynamics of 2,000 spins or 3,000 spins distributed over an hexagonal lattice to mimic what happens in vanadium-based Janus TMD monolayers. So we get this dynamic equation with some thermal field here to model the impact of thermal fluctuations. So the first step is, of course, to look at the ground state of the system without thermal fluctuations. And depending on the different behavior, I will not enter all the details here, but depending on whether you apply the field in plane, out of plane, and whether you consider the, vanadium, selenium, tellurium, or vanadium, sulfur, selenium, you can get a chiral spin spiral. It's chiral because you have Dzyaloshinskii-Moriya interaction. In the case of the in-plane configuration here, you even get some bimeron lattices. In the case where you apply the magnetic field out of plane, you can go from spin spiral to a skyrmion lattice. In the case of sulfur selenium, it's already an out of plane system. So an out of plane system, so then you can get only the skyrmion phase diagram. So here you have the magnetic field, and here you have the effective energy. Now, this is just the ground state. What we want to see is how robust those different states are. So we take a given state. So here you have a bimeron lattice, here you have a Scherman lattice, and here you have another Scherman lattice, depending on the configuration. And we basically turn on thermal fluctuations and see how the crystal, or how the magnetic phase evolves under thermal fluctuations. So from that we can reconstruct the full magnetic phase diagram. So depending on the magnetic field and on the temperature. So we can get those different phases. So again, if I just take the vanadium, selenium, thorium with in-plane field, at small enough magnetic field, I can have a transition from a spin spiral to a bimeron phase. And if I increase the temperature, I'm going to transit toward what we call the fluctuation disorder phase. And then at even higher temperature, a paramagnetic phase. So this fluctuation disorder phase is basically something where you do not completely lose the order, but fluctuations are so strong that if you look at the topological charge, you lose everything. Yeah. Okay. So the topological charge quantifies the number of chiral quasi-particles that you have in the system. So in the case of vanadium, selenium, tellurium, you see that you have the topological charge of 4, which means that you have 4 bimerons per unit cell here. If you go for the vanadium, selenium, tellurium with out of plane field, then in the Scherman phase, you're going to have, you actually have here -4 topological charges for the Schermions. And now you see that you actually, the topological charge actually survives even in the fluctuation dissipation region. So that's why this is a good indicator of what's happening, but you still have some chirality in the system. That's really what it means, which makes sense because you still have Dzyaloshinskii-Moriya. You really lose the chirality when the thermal fluctuations are super strong. So I would like to finish this presentation by addressing another system where Dzyaloshinskii-Moriya is completely different. And this system is iron, germanium, tellurium, which has this crystal structure. So the red points here are the iron. So you see that you have one in the center, and you have two that are symmetrically positioned with respect to the mirror plane here. So it's a system that has a mirror plane. It doesn't have inversion symmetry. Okay, so you would expect that indeed there should be something happening in such a system. And indeed, I would say probably a year and a half ago, there were this bunch of papers of this series, sorry, not bunch, apologize, this series of experiments showing that, I would say, reporting the observation of magnetic Schermion, even Scherman crystals in multi-layer iron, germanium, tellurium. And that was kind of surprising because those Schermions possess the Néel symmetry, so the symmetry you would expect at an interface. So it means that the Dzyaloshinskii-Moriya interaction that stabilizes those Schermions should be the one you would have to be similar to the one you would have at an interface. And the problem that if you look at the symmetry here, well, it doesn't look really like an interface. You actually do have a strong mirror symmetry that should very strongly impact the Dzyaloshinskii-Moriya interaction. I'm going to talk about that in 1 minute. So in principle, we could expect symmetry inversions in the some Dzyaloshinskii-Moriya because there is inversion symmetry breaking, but you also have a 6-fold improper rotation plus a mirror symmetry. So not clear. So what we did that we performed the point group analysis on the Dzyaloshinskii-Moriya interaction. At this stage, I would like to make one comment that I think is interesting, is that there is a connection from the symmetry point of view. There is a connection between the damping like torque, so the torque that is even in magnetization, and the Dzyaloshinskii-Moriya tensor. So this connection allows to derive this the tensor. The form of the Dzyaloshinskii-Moriya tensor just by looking at the form of the damping torque. So if you apply the symmetry, point group symmetry, on the damping torque, you obtain this kind of torque, which is the very same that I showed you previously. Okay, that's exactly the same torque you have in a C3V environment. Except that in the case of iron, germanium, and thorium, this is the only torque you have. Okay, because of the mirror symmetry, the feed-like torque vanishes, and the regular damping-like torque vanishes too. So the only torque you have is this C3V torque. And interestingly enough, this torque is associated with a current-driven anisotropy. You can actually demonstrate that this torque derives from an anisotropy, which is interesting because it's a non-dissipative torque in a sense. Now, if I make a connection between Dzyaloshinskii-Moriya interaction and the damping-like torque, so I can actually map the damping-like torque tensor on the Dzyaloshinskii-Moriya tensor in the limit of smooth gradient only. Okay, this is something that has been demonstrated by Framuth in this paper. And in this case, I can derive the Dzyaloshinskii-Moriya coefficient. Let me rearrange this tensor because it's a bit hard to see, and I end up with this Dzyaloshinskii-Moriya interaction. Now, the problem is that this Dzyaloshinskii-Moriya interaction is a total derivative. You see, so purely dx of this guy and purely dy of this guy. And if you actually look at its influence at the long range, well, it actually has no influence on the long range. We actually demonstrate that it even doesn't have an influence at the interface. I mean, you could expect that this one will give you some boundary condition and will induce some counting at the interface, and actually even that doesn't work. So we could say, well, on the long range, it seems that the Dzyaloshinskii-Moriya interaction of this system is definitely not the one you would have at an interface, completely different from what you would expect in a regular Janus monolayer or even at platinum cobalt interface, let's say. And unfortunately, it's not that interesting because it's a total derivative. So we wanted to go a bit further and then to perform again the spin spiral calculations. Okay. So we actually create three kind of spin spirals. Okay, so the spin spiral that is called the nail out of plane this way, a block type out of plane, and then an in-plane nail type. So this is the result of the Dzyaloshinskii-Moriya interaction. So here we just pass it, we distribute it into the contribution of each atoms. We'll not talk about this particular contribution. The take-home message is that the nail out of plane, so this one doesn't have an effective anti-symmetric dispersion. This one doesn't have an anti-symmetric dispersion either. If you sum everything, it's going to be 0. And the only one that has an anti-symmetric dispersion is the in-plane nail configuration. So it actually means that the only Dzyaloshinskii-Moriya we have, the vector is perpendicular to the interface, which is to the monolayer, which is completely different from what you would expect in at, let's say, cobalt platinum or at any interface. Okay, and that's because of the very strong symmetry, mirror symmetry. And most interestingly, this dispersion, this Dzyaloshinskii-Moriya only acts along particular direction. So if you, let's say, if you create a spin spiral, an in-plane spin spiral on this direction, for example, then you see that going from this atom to this atom, here you go through the red dot, and this way you go through the blue dot. So you see that there is a symmetry, a mirror symmetry that is broken along this particular direction, which means that you're going to end up with the Dzyaloshinskii-Moriya interaction that is out of the plane. But now, if you actually try to create a spin spiral along this direction, well, you see that the path to go from, let's say, one atom to another is completely symmetric on this side compared to this side. So here you have no Dzyaloshinskii-Moriya interaction. You can only stabilize a spin spiral along this particular direction. So you do have a Dzyaloshinskii-Moriya interaction, but it only acts on planar systems along particular directions. And the problem is that iron, germanium, and thorium has a strong out-of-plane anisotropy. So not much change to observe anything interesting at this stage. Of course, if you engineer the anisotropy, that's another story, and then you can imagine to indeed see some long-range spin spirals in the plane. But we're not there yet. So I will stop my presentation here. Thank you very much for your attention. I'll be very happy to answer any questions.
Open for question. Oh, there's a first thing maybe from question from the QA.
Yeah.
Thank you for the next talk. Does the map between the DMI and the SRAM talk format or fundamental? It's formal.
That's a great question. I think it's actually a very important point. So you know, you have at least 3 ways to calculate Dzyaloshinskii-Moriya interaction, at least. So this connection applies. I mean, you can demonstrate the connection analytically only in the if you use the Kubo formula for Dzyaloshinskii-Moriya interaction. Okay, so it doesn't. So it's only the long range approximation. So if you consider that you have a small gradient, a smooth magnetization gradient, then you can derive, and this is what was done in this paper. We also have a paper recently where we derive it in a different manner and obtain the same formula. So if you derive the Kubo formula for Dzyaloshinskii-Moriya interaction in the long range, so in the smooth magnetization gradient, then you obtain a Green's function formula that is similar in terms of structure, structurally similar to the Kubo formula you would obtain for the damping light torque. Okay, so in this context, there is a direct correspondence. It doesn't mean that they are equal, okay, because in one case, you have the integration is not the same, okay? but the structure of the Green's function is the same. So from the symmetry point of view, the symmetry should be exactly the same, but that's only in the smooth gradient approximation. Now, if you calculate Dzyaloshinskii-Moriya using the let's say the generalized block theorem, or using the real space spin spiral, which is what has been done by Hongqing Yang and Madibek Chief, for those who are familiar with their work, then you cannot make a connection because you are doing it in a completely different manner. And this kind of Dzyaloshinskii-Moriya only works for short range spin spirals. I hope I answered your question reasonably well.
Yeah, thanks for some. Any more questions?
I guess Germans are interesting if they can be moved in a controlled way, so additional electric field needs to be considered. But could electric field help also in generating skirments? Oh, hi, Stefan. Just one thing, the electric field you're considering is a perpendicular one, like a gate voltage, or a torque induced, or whatever, like. Okay, so I think what you, I mean, there've been a lot of studies on that, and I'm not that much an expert, but I would say if you want to generate a skirmion, you basically have to reach a certain compromise between the anisotropy, the exchange, and Dzyaloshinskii-Moriya interaction. So of course, if the ferromagnet, if the exchange is very, very strong, then you basically kill any possibility to generate a chiral structure. So what can be done, though, that if you apply a gate voltage, you should be able to control the anisotropy, reduce the anisotropy, and then nucleate a skirmion by injecting a current. So maybe, yeah, this kind of combination, I think, is possible. I'm not sure it's very easy to do experimentally, because you need to have ion liquid gate voltage, for example. But I think this could be definitely an interesting way to go. Can you talk about the microscopic origin of the damping light and DMI in these low dimensional systems? So everything is connected to the. I mean, from my point of view, at least, is connected to the orbital hybridization. So this is what we try to do in this effective model here. So basically, what happens is that what happens here is that your dz square orbital will be coupled to the PZ orbital, and that's what drives all the physics. Okay, which kind of makes sense. I mean, it's the perpendicular PZ orbital will couple to the DZ square orbital, will change its energy, and the planar orbital will be coupled to the perpendicular orbital through the PZ orbital. I don't know if you follow me, but if you want to have a Rashba spin-orbit coupling or a Dzyaloshinskii-Moriya, again, if you just think in terms of Rashba is at the source, is at the source of everything. If you want to have a Rashba spin-orbit coupling, you need to find a way to create a mixture of d orbitals on the vanadium atom that fulfill this kind of relation. So, for example, if you want to have an SX component, then you need to mix dz square with dyz, and you can do that through the pz orbital of the top atom. Now, of course, if the coupling between the top and the bottom atom is completely symmetric, then you lose the advantage. But if you make it asymmetric, then you end up with a coherent superposition of dz square with dyz, and that will give you an SX component. So that will give you a Dzyaloshinskii-Moriya a Rashba spin-orbit coupling. I would like to, I'm sorry for this publicity, but I'd like to encourage you to have a look at, I'm getting there, at this paper here. Okay, this one, actually those two papers here, where we actually developed a toy model with only p orbitals to explain how Rashba spin-orbit coupling and Dzyaloshinskii-Moriya can emerge from inversion symmetry breaking and the coupling through the pz orbital of the top atoms. Okay, I think if you have this minimal model in mind, then you can understand where the macroscopic physics is coming from. Oh, Shahid is here. Hey, Shahid. So Jose, is the Kubo formula for DMI associated with an electric field? No, the idea that's it's not with an electric field, it's with the again, you have a detail in this paper here. You basically, I start from Keldysh formalism and I expand my lesser Green's function in the first order in the gradient, in the magnetization gradient. So you basically consider that you have a small magnetization gradient and calculate the magnetic energy of the system to the first order of the small magnetization gradient. So in a sense, the role of the electric field is replaced by the magnetization gradient. Is there any other torque that can be expressed with, as an anisotropy? Oh, that's a very good question. I think yes. There is a long list of torques. I should have put the reference here by Jakub Żelazny. I did a fantastic work where he actually went through all the point groups that could be interesting for, I mean, the non-centrosymmetric point groups, and derived the damping-like torque in those cases. So I believe in some cases, it's possible to associate, only in some cases, to associate a damping-like torque with an anisotropy. That's actually a very good point. This is something that we could look into very quickly. I will send you the reference, and then we can carry on our discussion. Shahid, how Rashba effect in Janus monolayers is different from Rashba achieved by interfaces? That's a very good question. If the block state is controlled by the gamma point, okay, so if the transport is mostly gamma point, it means that the Rashba you're going to have is exactly the same as the Rashba you're going to have at interfaces, at sputtered interfaces, sputtered interfaces. So interfaces where you basically lose the in-plane symmetries. Now, actually, if you consider, let's say, this kind of system here, of course, you're going to have a 6-fold symmetry, a 3-fold symmetry, plus mirror, and so on and so forth. So then the Rashba effect should have deviations from the regular Rashba effect. And in a sense, this is what you have in this picture here. You see, close to the gamma point, your Fermi surface is spherical, but a bit away from the gamma point, your Fermi surface have this hexagonal warping. So that's where you're going to expect some deviation from the regular Rashba spin-orbit coupling. Of course, you could imagine to find material that are completely, whose transport is completely dominated by the K points, or, well, maybe the K point is a bit extreme, but I would say, you know, by state that are a bit away from the gamma point, and in this case, you might indeed see some distortion of the spin momentum locking. And this is actually what we have observed with Jose in this manganese and vanadium-based Janus monolayers. Stefan, is spin the result of a self-rotation of the electron? Yes. Of course, spin is a quantum degree of freedom. It's a plus 1/2, minus 1/2. I mean, it's a quantized quantity. What is beautiful is that at the end of the day, because spin creates a magnetic moment and couples the magnetic field, you can build this this connection with the Magnus effect. But this is just because you have the Zeeman effect. I think because of the Zeeman effect, then you can make a comparison, or you can make this you can find similarities with the mechanical Magnus force. And at the end of the day, they are all angular momentum. So because they are all angular momentum, you have angular momentum conservation. So I would say from this point of view, as long as spin is an angular momentum, which is the case, then it works. So how can a single electron with both spin up and spin down respond to strong spin-orbital coupling? If spin Hall effect not possible for a single electron wave? Ooh, I like those questions. The spin Hall effect purely semi-classical. I would say the picture we have of the spin Hall effect is purely semi-classical. That is clear. But you can of course see some, if you just take one way, you know, you use quant, for example, and you calculate, or even actually your code, you calculate the anomalous velocity for one electron, you're going to find something. You're going to find some skewness in the transport of your wave function. But this skewness will be different from the spin Hall effect we all expect, because spin Hall effect only arise in the semi-classical limit. I mean, the one we are used to, you know, where you have spin accumulation on each side of the device. This one for me is a semi-classical effect. So you need to transpose the quantum mechanical information into semi-classical physics. And there is well, I don't know if this is a good answer, but I think this is I mean, your question is of course very profound. How can a single electron with both up spin and down spin respond to a strong spin-orbital coupling? Well, I would say this in my mind. So I would say it depends how strong it is. So do I understand properly that strong spin-orbital coupling means that the spin is not a good quantum number anymore, and you should consider the total angular momentum? Is it what you mean? Okay, so total angular momentum. That I think it's a great question. You should be able to observe. In my mind, you will still observe a spin-orbit torque effect and something that looks like the spin-orbit physics that we are used to in the small spin-orbit coupling limit. Because at the end of the day, of course, you end up with with the momentum that is L plus S. It's not, I mean, it's J. It's not just the spin. So in a sense, talking about transfer between L and spin, I mean, between orbital and spin, doesn't really make sense anymore. However, if the magnetization, I mean, the magnetization of your system with strong spin-orbital coupling, and take your magnetic uranium, for example, then the magnetization will couple differently to the spin and orbital motion. So you might still have a way to manipulate magnetization via spin-orbit coupling in the strong spin-orbit limit. Of course, in the infinite spin-orbit limit, then it doesn't work anymore because you only have one J, so there's no transfer. But that's actually a limit that I would like to explore. I think it's a great question.
Okay, and more questions? Okay.
Yeah, can I ask a question? Yeah, Aurelien, thank you for your very nice talk. Yeah. Can you comment either Janus beside the vanadium? about the strong strengths of the spin orbital coupling as well as the spin orbital torque
in other materials.
Other transition metals. Yeah.
Okay. So the problem I see with the TMDs is that magnetism is always carried by light atoms. I mean, fairly light atoms, vanadium, iron, cobalt. So of course, spin-orbital coupling is there. It's decent. It's not gigantic. And the only strong, I mean, the role of tellurium, even if tellurium has some pretty strong spin-orbital coupling, stronger than cobalt, actually the role of tellurium will be to desymmetrize the wave function. Okay. Now, in terms of other materials, we have been really scratching our heads to find new platforms, because actually something I really would like to thank you guys, especially the experts in the assistance in the that didn't, so in the attendance, that it didn't jump on the very big flow that vanadium-based Janus monolayers, vanadium-based monolayers are actually not magnetic at room temperature. They are actually, there have been a lot of debate about that, and it seems that actually charge density wave takes over. So we actually realized that, well, at the end of our project, so unfortunately, that's quite unfortunate. Now, the thing that realistically, you can always stabilize, you can always have at the substrate and try to stabilize the magnetic phase. So I think there's still a chance that we can engineer that.
Yeah, because of the CDW clinch, the magnetism.
But I think the CDW, of course, is super important. And the problem is that it's very hard to identify with DFT. Because
I agree.
You should treat very, very large supercells. So I think that's one of the biggest question that needs to be addressed honestly when we carry on DFT calculation, is the fact that there's just so much we can say about those systems. We cannot really investigate, or we do a full study about charge density wave, but that needs to be done with in collaboration with experimentalists, because of course we cannot always model gigantic supercells and vary the length of the size of the supercell. This is computationally it's too demanding. So that's actually one very big question that remains open in my mind. Now, if you want to consider all the materials, currently I think we need to follow experimentalists. I think it's super hard because of this CDW, or the charge density wave issue. I think it's I would tend to take predictions with extreme care, because we have seen huge number of predictions about magnetic two-dimensional systems. And as a DFT expert yourself, I mean, you know that probably half of them must be taken with great care, let's put it this way. And that makes sense, because it's impossible to look at CDW. So maybe they actually are stable in CDW and not with ferromagnetism. You even have systems where CDW coexists with ferromagnetism. So I think it's fantastic from the computational point of view. There's really a lot to do, but from the perspective, in terms of prediction of new materials, it makes things much more challenging. Currently, the most successful one, I think, is iron, germanium, tellurium. There is also chromium, germanium, tellurium. It seems to me that the halide, the trihalide, are usually have a Curie temperature that is below room temperature, so it's probably not the way to go. Transition metals like dichalcogenides are still an interesting game to play. And maybe actually a bilayer or trilayer would be sufficient, because we focus on two-dimensional because of course it's more intellectually fulfilling because we have the ultimate limit. But maybe if ferromagnetism is stabilized using a bilayer, maybe this is sufficient for application.
Yeah, I agree, because it's hard to see. It's hard to generate long-range ferromagnetic coupling in just single atomic layer, right? Yeah.
I think it is. Yeah. But the thing that I don't really know how to. There have been a lot of experiments showing that there is long-range ferromagnetism, but Yeah, I don't know how experimentalists could comment on that. You know, whether when they see long-range permagnetism on two-dimensional system, is it like super robust or is it super hard to get?
Okay, yeah, thank you very much.
So already I have one question. Okay, so Doppler's Blanche state is derived from the infinite crystal, right? So what the Blanche state looks like at the interface? You know, that boundary in the surface, like the boundary. Okay, very close to the boundary. Now it's not an infinite crystal potential, right?
Yeah, yeah. So what you're talking about, the spin-orbit torque or sorry?
That's you know, how the the Blanche state affect the spin torque, whatever. Okay, yeah.
The block state.
Yes, Blanche states.
Okay. So okay, so at the boundary, of course, you have symmetry breaking also at the boundary.
Yeah.
So you would expect that you should also have a Rashba, but in the other direction. Now, I don't know if this is very robust. That's, I mean, we know that in transition metal heterostructures, it is super robust. You can have it as scrappy as possible, and it is still working. Now, if you talk about the boundary of a two-dimensional crystal, usually I don't know how clean is this boundary. If this is very clean, then you might indeed have a different form of the torque, and then you should be able to nucleate domain walls with this new torque. That could actually be interesting, because if you think about a boundary, the symmetry breaking is toward the center of the crystal, or out of it. It doesn't matter. It's perpendicular to the boundary. So this actually can create a Rashba effect with a field that is perpendicular to the plane. So this could actually, help to nucleate magnetic domains. But even from the magnetic point of view, the magnetism at the boundary will be modified because the anisotropy is different, because Dzyaloshinskii-Moriya is different. Then you should be able to nucleate domains. So I don't know if there is any fundamental difference compared to just the edge of a pattern media, for example.
Okay, thank you.
I have a short question, Aurelien. Fantastic talk, by the way. So when you, with the atomistic simulations, you had predicted a skyrmion phase. How large are these skyrmions? Are they sort of atomic scale? And also, are they in some way tied to the crystal lattice?
What do you mean tied? When you say to the crystal lattice?
As in, is there any orientational, kind of like the iron iridium system, where there was a sort of lattice matching between the skyrmions and the atomic lattice, basically.
Oh, I see.
Is it that kind of system, or is it more like the multi-layers?
I'm not very familiar to the iron iridium, because it's a very unstable system. So we actually we spend a lot of time and energy to try to understand what was going on in this iron iridium. But iron iridium is very, very, very peculiar. Because magnetization of iron actually is quenched when you put it on the top of iridium. So it's a very specific kind of an accidental system for me. But so the skyrmion we see, let's say here, I think you have something like I think it's like something like hundreds of spins. I think so. It's hundreds of I think let me check. Yeah, I think it's 100 of lattice parameters. So it's probably around 20 angstroms. So it's not a nano skyrmion, okay, but this is still a fairly small skyrmion. That's also because the exchange is actually fairly small. It's again the only magnetism is coming from vanadium. So vanadium is a weak magnet. So basically everything is weak. The exchange, the Dzyaloshinskii-Moriya, but because exchange is also weak, then you end up with a ratio between Dzyaloshinskii-Moriya and exchange that is not too bad, and then you can observe this thing. Now, what is I think interesting is the fact that at least in the vanadium selenium tellurium case, you have this hexagonal shape. So basically, the lattice symmetry is imprinted in the Skerman crystal, which is not the case if you take the vanadium selenium vanadium sulfur selenium, where the Skerman is more as a round shape. So I don't know if this answers your question.
It does, yes. Thank you.
Okay, and more? Okay, if no question, okay, I would like to thanks. Okay, Professor Aurelien. Okay, Manchon again. Okay, thanks for a nice talk. Okay.
Thank you very much, guys. Thank you.
Thank you.
Yeah, thank you.
Thank you.